Okay, hello everyone, welcome back. So last time I talked about the linear regression. I give you several examples. Firstly, I give you this one feature example. If we want to predict the house, the price of a house, we can use the area as the feature. And I just tell you what is the model directly, and we can visualize it as this one. And of course, if we have two features of a house, we can predict the price of a house by these two features we have here. And the model, linear model we have, can be visualized as a plane or a hyperplane here. Of course, we can have as many features as we want. So if we have more than two features, we are not able to visualize it. So our prediction will be called as the hyperplane here. And the linear regression is also the basic for the neural network learning. And this is why the linear regression is very important. So in this video, I will go through a calculation on how to find these models, specifically on how to find these weights of omega here. Okay, so let me write the title first. Linear regression 2. Okay, let's get to the topic here. So in this video, we will mainly talk about how the model, specifically the weights omega, how the weights is found or determined. So it is not determined arbitrarily. It is determined on some mathematical equations or functions here. Okay, the answer I give to this question is that the model is found by optimizing the loss function. So you may or may not have heard the term loss function, but you must have heard one term, maybe error. So the loss function is just a measurement of error here, but we have a terminology for this error function as the loss function in machine learning. So we will get this model by optimizing the loss function. And then I will also start with a very simple example, and this is the example we are using for all these videos here. So the examples is something like this. It's also the prediction of a house. So here we have only one features because it's easy to visualize and easy to calculate. And xy is the area of a house, and the y-axis is the price of a house. So differently, now I will give you some tuning points and their coordinate here. So this one is 100. You don't need to care about the unit here. This is just for demonstration. So maybe you can imagine this as 100 square meters or something. So we have 200, 300, 400 here. Okay, for the price, we'll also have some ticks here. 20. So you also don't need to care about the unit here. Maybe it's $20K, 20, 40, and 60. Okay, suppose our training data is something like this. We have a house whose area is 100 and its price is 20. So this one, the coordinate for it is 120. And then we have another house whose price is 60 and its area is 200. So the coordinate for this one is 260. And we have a third house whose area is 300 and its price is 40. So its coordinate is 340. You may feel very confused that why this house is cheaper than this house, but its area is larger, right? It has larger area, but its price is cheaper. You don't need to also care too much about that, because now we just have one feature of area. Maybe the location of this house is not as good as this one, so that is why this one has lower price here. That is why we need more features. Now we just have one area. So the purpose or our task is to find a linear model to fit these two data points. So here, these 3 points are all training points here. We have talked about what is training point and what is testing point. So these 3 points are just training points. So this is a very small data set. We only have 3 training points here. Okay, we just put it like this, and we will assume we will use linear regression to predict this problem. So as usual, I will use y hat, but differently, I will put n, a subscript of n. So this n means the nth data or sample. So here in this problem, in this simple example, we have 3 houses. So here n will be equal to 1, 2, 3. That's it. Very simple. And this one equals to our weight transpose and multiply with xn. So here xn is not a number here. This one is a vector. Whose vector? This is the feature vector to the nth sample. Also this one. So xn is actually a vector. Belongs to the nth sample here. So you should pay attention to the notations here. You may get confused here. And where omega equals to omega 0 and omega 1. So we have this bias term, we have this weights here. Okay, and omega n equals 1 as usual, as we said. So the first number of our feature vector is 1, because the 1 will be multiplied with this bias term. And the next one is our area. So, but now here I will write it a little bit differently. I will write this as n1 here. So here, this n, as usual, so this is the, means it belongs to the nth sample. And what is this 1? This one is just in case we will have more features in the future. So this one means the first feature. Because in this example, we just have the area as our feature. So it doesn't matter if it's the first feature or second feature, because we don't have the second feature here. So I just put this one because we may have more features in the future. Okay. And then we will define our loss function as this one. So our loss function, I define it as the residual sum of squares, or RSS in short. So this is our loss function, and I will write it in this way. So it is RSS. I will put a bracket in omega. So this means this residual, this loss function is a function of omega. So if omega is changed, the loss function, the value of loss function is changed. This one is equal to, so as the name implies, this is a sum of squares. So it is a sum of squares between our prediction and our ground truth. So I will write and I will explain here. So y hat n is our prediction, right? And our prediction minus yn. So here, what is yn? So yn, I call it ground truth. What is ground truth? So ground truth is this one, is our tuning data, tuning point. Is this 20? Is this 60? Is this 40? So this is the real price of this house, not our prediction, right? So I make a minus, and I take a square. So you can see that this is yn and between n. So n is the n sample. So here you can see we have 3 samples. So we need to sum them up. So this is a notation for the summation. So n equal 1 to n. So in this specific example, what is n here? So n is just 3, but I will keep the n here. So n is number of data here. So in this example, we have 3. So the capital N is 3. So this is the loss function we defined. So we can find this loss function makes sense because it will measure how good our model behave on our data. Because you can see this is our prediction. We use our prediction value to minus our ground truth, and we take a square, and we sum them up. So we will need to minimize this one. So the best model we will have is that we can minimize this loss function here. Okay, I can rewrite this. I can continue to write this. So this one also keep the same, because we know what is y hat here, right? So y hat is this one. So I will substitute this one to this equation. It's very simple here. And I keep the ground truth the same, and I take a square here. Okay, so because in this problem we just have one feature here, so we know what is omega and what is xn. So I will substitute this omega and xn to this equation here, and equals to 1 to 3, because we just have 3 data, right? 3 samples. And so I put this one. So this is an inner product. So this one will goes to something like this. Okay, so now you should pay attention that this one, and this one, they are not vectors now. They are just numbers or scalars here. So they are there are some real numbers here. Okay, let's continue. So I will just write my loss function to this form. I will maybe make it a little bit more clear. Okay, I will just keep my loss function as this one. So we know that if we want to minimize it, so we need to take derivatives. So we need to take derivatives. So let's get back to think what parameters is what we want to minimize. So this is the weights, right? So these are two parameters, two weights that we want to minimize. So we want to find. So we have two parameters here, which is omega 0 and omega 1 in the loss function. So we need to take the gradient to this loss function. So we will take the partial derivative of loss function omega with respect to firstly omega 0 here. And next, we also need to take the derivative of loss function with respect to omega 1. Because omega 0 and omega 1 is two weights we want to find. So we need to differently take the partial derivative and set them to 0. So next is something I will do. So it's just something about the partial derivatives. So we take a partial derivative of this one with respect to omega 0 here. So we will use the chain rule. So this one, it will go to the beginning, and I will keep the summation notation here. So if we take the derivative to omega 1, so omega 0. So this is the partial derivative with respect to omega 0, and I will set it to 0 here. So because here I'm taking the derivative, so this one I will put a star notation here, means that once I got this omega 0 star and omega 1 star, it will be my optimal weights here. So here I will also take the derivative to the omega 1. So it's very similar. So the difference is that when we use chain rule, firstly we take a derivative of this square, and we will find that inside of it there is a weight here. So this one will also be considered here. It will be multiplied here, and so you can actually practice this on how to use the chain rule to get the derivative. It's something you learned when you are an undergraduate student, and this is very simple here. So if we have this term, so I set this 2 partial derivative to 0, so this 2 means nothing here actually. And let's organize them, just rewrite them as this one. Okay, this is the first equation, and this will be the second equation we have. Okay, so we have reached to this one. And then I will just expand the bracket here. So this is a summation over n. So we can find this term is not related to n. So we can write these two equations as this one. So this one, firstly, is 3 multiplied with omega 0 star. And we can have this one. Because this omega 1 is not related to n, so I can write it in front of the summation notation here. And so here I will move this term to the right hand side. So it equals to, so I can write this first equation to this one. Also similarly, I can write the second equation here. Because this omega 0 is not related to n, so I can write it in the front of the summation. And we will also have this one. And I also move this one to the right hand side. Okay. So these two terms are all related to n, so I put them inside of this summation here. Okay. After we got this, we can find this is a linear system, and these are two equations, and we can find there are some common terms here. This is the weights we want to find by using these three tuning points. So the next thing I will do is to rewrite this one to a matrix form. So you can get some practice here, and you can also practice yourself. So if I want to write these two equations in a matrix form, so it can be written in this way. And they will multiply with our optimal weights. It will equal to the right hand side. So right, this makes sense because when you use the first row multiplied with these weights, you will get this term exactly. Okay. So now, at this moment, you may get very confused, or you may have already quitted this video because now it seems very boring. But next, it's the magic will happen here. So this process is actually what is happening behind the linear regression problem, because we have these 3 points and we want to find the weights that can optimize our residual sum of squares. So next is the magic will happen here. So we can see that what are those x and 1 here, and what are those yn here. So this one is x1, x2, x3. So here y1, y2, and y3 is this 20, 60, and 40, right? It's the ground truth. It's the price of our house. So this one, these are yn, we already know. It's the tuning point. And what is x and 1? So x and 1 is our feature, right? It's our feature here. It's our area of the house. So it is already known by the training data. It is 100, 600, and 200 and 300. So this one we know, this one we know, this one we know. So the only unknown is these two. So we can solve this equation. So next, let's solve this equation. So this one is 3. So this one is we sum the area of those houses. So this one is 100, and we sum 100 with 200 with 300, it will give us 600. Of course, this term is the same. And this one is just you take a square of the area and then you sum them up. I have do the calculation and I will write the numbers here. So this is this matrix, the first matrix here. And the second matrix, we don't know. We want to solve it. In the right hand side, so this one is that you need to sum the price of those 3 houses. So you sum 20, 60, 40. It will give you 120. And also this one, what is this one? So this one is you multiply the price with the area and then you sum them up. So you can do the calculation. I have done it. So you will get this value. So you can see this very complicated matrix. We already know the information here. What we don't know is what we want to solve. So then we can solve this problem. So this is a simple matrix calculation. We will need to calculate the inverse of this matrix. So this one, the weights will be equal to the inverse of this matrix and multiply with this right hand side. So this will be very easy. You can calculate it using Python or MATLAB. I have calculated, so the inverse of this matrix is 2.333. Okay, this is the inverse, and you use this inverse multiply with the right hand side. And you can get the weights here. So the weights is 20 and 0.1. So you get this model. So what is our model we get? Thus, so this one is the bias term. So I will use this one, omega transpose, and multiply with 1, omega 1. So you will have 20, 0.1, x1. It's just a linear equation, right? It's just an equation. So we can visualize this one on this diagram. So the intercept is 20. So this is the intercept. And we need another point. So we can calculate what is the price when the area is 400. So when this one is 400, so the price is 60, right? So another point in our prediction is here. So we have 2 points. We can draw a line. So this is the model we finally found. You can find that our algorithm has told us that this hyperplane can minimize these arrows here, can minimize this arrow here, and it can minimize this arrow here. So any other hyperplane, any other prediction, maybe this one or this one, will have a bigger arrow than the green line here. So that is how we find this linear model here. So actually this is what is happening behind the linear regression problem. Of course here we define the loss function as the residual sum of squares, RSS. You may ask, can you use some other loss functions? The answer is yes, you can use. But this one, RSS, is more commonly used. Of course, you can define the loss function as the absolute error. For example, this one. Yeah, it's the absolute value between your prediction value and your ground truth. And you optimize this one. Of course, you can also use this one, but the sum of squares is more commonly used here. Okay, so I think this is all the contents I want to cover in this video. We use this example to help you understand how we can find the optimized weights omega here